In this section we will discuss the channel models. First we'll discuss the channel models used in fixed wireless networks, in particular the Stanford University interim models. Next we will discuss the channel models used for mobile wireless networks, for example for 802.16e, in particular the COS 231 Hata model. First, let's discuss the channel models used for fixed wireless networks. A great reference that summarizes these models is provided here, a comparison of empirical propagation path loss models for fixed wireless access systems. Although it is for fixed, it gives a nice summary of the COS 231 model, Hata model also. And we'll draw from this reference. And then we will actually refer to some other more detailed references and get some more information, in particular the cases for modeling the micro effects. The Stanford University interim models defines three types: a type A, a type B, a type C. For type A, which is the maximum path loss, it is appropriate for hilly terrain with moderate to heavy foliage densities. Type B is for mostly flat terrains with moderate to heavy tree densities, or a hilly terrain with light tree densities. And type C has the minimum path loss and applies for flat terrain with light tree densities. At this point we are dealing with the macro model effects, that is path loss. Then later on we'll talk about the micro effects such as fading due to multipath and Doppler, for example. But for now we're looking at the overall path loss from the base station to the subscriber station, whether fixed or mobile. Here we show a type A scenario where we're dealing with heavy foliage and also hilly terrain. This has the maximum path loss. Type B is for either flat terrain with trees, with a high density of trees, or for example a hilly terrain with a lower density of trees, and this is sort of in between. Type C is for flat terrain with low foliage or low density of trees, and this might be an example of that. In this case you see that there aren't that many obstructions from the potential sites where we have the subscriber stations back to the base station. This is the important formula for the path loss for the Stanford University interim model. And again, this is the path loss from the base station to the subscriber, and as for the macro model, it does not include effects for multipath or Doppler, for example. So the path loss is expressed by this expression here, and it has different components that I will discuss in detail. For example, the component A, which is shown over here, depends on the wavelength and incorporates the effects along with D, the distance of the free space loss. However, as you get away further and further from the base station, you have to include the effects which are incorporated into this coefficient gamma, which take into consideration the terrain and also foliage and tree and obstructions. So for example, A depends on frequency over here, and so do other terms like X of F. D sub 0, which is set to 100 meter, is a fixed distance, and D of course is the distance to the base station, from the base station to the CPE or customer premise equipment. The term S is a log normally distributed factor that is used to account for shadow fading owing to trees and other clutter, and has a value between 8.2 dB and 10.6 dB. Now gamma is the important parameter that takes into consideration the three types of terrain that we mentioned: terrain A, terrain B, or terrain C. And it depends on the antenna height of the base station. So H sub B is the base station height above ground in meters, and is between 10 meters and 80 meters. So it could be, for example, on a tower. So if we look at the factor gamma, gamma of course multiplies this factor here, which depends on the distance to the base station, and amplifies it. And it depends on the terrain. For example, let's take the case of terrain A, which is for maximum path loss, which is like a hilly terrain with lots of foliage, lots of trees, a lot of obstruction. So in this case, A is 4.6 dB over here, B is 0.0075, and C is 12.6, and gamma depends on the antenna height. As we see here, for gamma, the larger the value of gamma, the more the path loss. So for example, we see that for terrain A, we got a 0.6 dB more loss than the case for terrain B, and for terrain C, there's about a dB difference between the two. Also note that as we increase the height of the base station h sub v, then gamma decreases, and we get less path loss, which makes sense the higher the base station antenna is. Let's take a look at this factor C over here. We see that factor C is affected by the terrain type quite a bit. We say for terrain A it's equal to 12.6, and for terrain C, where we have less obstruction and we have flat terrain, that it's equal to 20. And this shows that the higher the value of C shows that and notice that this is a positive, so this term actually increases gamma. Increasing gamma causes more path loss. But the point is that for terrain type C, the higher the value of C, that means that as we increase the height of the antenna, we get a much stronger reduction in the value of gamma when dealing with terrain type C versus terrain type A, where increasing the antenna height due to the fact that it is hilly, for example, or there's a lot of foliage and trees that obstruct the view of the antenna, that the effect of increasing the antenna height is less than the case for terrain C, where if we increase the height of the base station antenna, then we reduce the path loss considerably, and that is shown in this equation over here. So we can compute gamma based on the type of terrain, and let's go see how we compute x of f and x of h and how they depend on various factors. So here we have the same equation as we had before with x of f and x of h. X of f depends on frequency, it's the frequency dependence, and also recall that a depends on the frequency because it depends on the wavelength. But x of f depends on the frequency in this sense, so that as the frequency increases we have more loss in the path loss. X of h is the dependency on the CPE antenna height. So for terrain types A and B, we compute it using this expression here, and for terrain type C we use this expression over here. Notice that for terrain type C we use minus 20 dB, so there's about a minus 10 dB improvement in path loss. We have less path loss for terrain C, which was, as you recall, for flat terrain and low foliage. Also note that as we increase the height of the CPE, or customer premise equipment, or the subscriber, as we see over here, as we increase h sub r, then the total path loss decreases, which makes sense. The higher the antenna for the CPE, the less the path loss. So this expression encapsulates many of the issues involved with the path loss and dependency on various parameters, including the distance of the CPE to the base station, the height of the base station antenna, the height of the CPE or subscriber station antenna, and also effects of the terrain and the various types of terrain, for example, type A, type B, type C. Also included is the dependency on the frequency. After we compute the path loss based on this model from the base station to the CPE or to the subscriber station, we have to take into consideration the effects of fading due to multipath and also Doppler, and we'll discuss that later on. For more detail, I'll refer you to Vinco's papers, both submitted in the IEEE Journal of Selected Areas in Communication, along with Greenstein, and also a paper by Vinco and Hari, which was submitted to the 802.16 Broadband Wireless Access Working Group back in January 2001 in order to get more detail. The next model we will discuss is the cost to the -231 Hata model. This model is very appropriate for mobile environments and is widely used for predicting path loss in mobile wireless systems. It is an extension of the Hata Okumura model and contains corrections for urban, suburban, and rural flat environments, and is appropriate for frequencies between 500 megahertz and 2 gigahertz. Also note that COST stands for European Community Collaborative Studies in the area of science and technology, for your information. In the COST model, again, we have the path loss from the base station to the mobile station. And again, this is a macro model effect, so we don't take into consideration here the fading due to Doppler or multipath. That has to be added to the path loss. So you compute the path loss and then you incorporate the effects of Doppler and multipath fading. Now the path loss depends on frequency as shown over here, so the higher the frequency, the more the path loss. It depends on h of b, which is the base station height above ground in meters, so the higher the base station antenna, the less the path loss. It depends indirectly on the height of the mobile station antenna or the CPE antenna through the parameter a h of m. It also depends on the distance shown over here. So d is the distance from the base station to the CPE, and cm is defined to be 0 dB for suburban and open environments, and you add 3 dB of loss for urban environments due to more scattering and more obstruction. So let's take a look at the parameter AH of m. So AH of m is computed according to whether the environment is an urban environment or a suburban or rural flat environment. So for frequencies above 400 megahertz, we use this expression over here. And you notice that it depends on h of r, which is the height of the CPE antenna above ground in meters, or the mobile. Obviously, the higher the antenna height for the CPE, then the path loss decreases, as we see here, because we're dealing with minus h of m. And here, as h of r increases, then we reduce the path loss, which is as expected. Note that the case for suburban and rural environments, we also have a dependency on the frequency, f. But for the case of urban environments, it only depends on h of r, assuming that f is greater than 400 megahertz. So in summary, using the COST-231 Hata model, we can compute the path loss given the distance to the base station, the height of the base station, the height of the CPE, and given the frequency. For more details, we give you references over here. These two references provide more detail into the model that we're using for mobile, the COST-231 Hata model, and refer you to these references in order to get more detail. However, based on what we provided in the expressions above, you can actually calculate the path loss suitable for urban or suburban or flat rural environments for a mobile type of situation. Now, as we mentioned before, the Stanford University interim model that we discussed before was for the macro modeling effect, the macroscopic effect, which was the total path loss from the base station to the CPE or subscriber station. But over here we actually talk about the channel model specific to statistical parameters of a microscopic effect, which are fading due to multipath and antenna directivity, and of course Doppler effects. Multipath is modeled using a tap delay line, and we'll discuss that in a minute. As a reference, please see this submission to the 802.16 working group, which was done in 2003. Again, the Stanford University interim model defines three types of terrains, A, B, and C, as we discussed before. Recall that type A was hilly with a lot of foliage, type B with either flat with heavy trees or a hilly terrain with less trees or less foliage, and type C was flat terrain with minimum foliage or trees. Here we define 6 SUI models, and they're grouped according to the terrain types as shown in this table here. Also, we'll discuss the K factor, When you have a K factor that is low, you're dealing with mainly non-line of sight type situations where the CPE or subscriber station does not have a line of sight directly to the base station antenna, and most of the signals that is received is due to multipath and scattering. For a high K factor, we assume that there is a direct line from the base station to the CPE or subscriber station. In this case, two of the models correspond to high K factors and with low Doppler. In the case of low K factor, we have a case where we have low delay spread and high delay spread, as shown here, or high Doppler effects or lower Doppler effects, categorized as moderate delay spread or high delay spread. Now here's a scenario for the modified Stanford University interim channels. One is that the cell size is about 7 kilometers, that the base station antenna height is 30 meters, and the receive antenna height at the CPE is 6 meters, and the beam width of the base station antenna is 120 degrees, for example. There are also other parameters that are discussed here, and we're dealing with vertical polarization. Here we show the parameters for SUI1 channel. Going back, we see that SUI1 was for terrain type of C and also for a high K factor, which means it has a line of sight back to the base station. So here we see that the K factor is high, and notice that for each channel we have 3 taps, and for each tap we define a delay and a power. For example, the multipath delays are indicated by taps 2 and taps 3 with associated delays. For example, the delay for tap 1 is 0, that's the main path. And if we have a direct path to the base station from the CPE, then we have a high K factor as shown over here. And of course the K factor is 0 and does not apply for tap 2 and tap 3. The power of tap 2 is minus 15 in this case, and minus 20, so the multipath from due to tap 3 is less than, of course, the multipath due to tap 2. This actually gives you the power delay profile, and you can compute the RMS delay spread using these numbers. Notice that the units are in dBs. Also notice that the delays are small, 0.4 and 0.9 microseconds. And this is, of course, makes sense. We're closer to the base station and we have a high K factor. Also, each tap has a different Doppler shown over here in Hertz. We'll talk about the Doppler effect shortly. Also, notice the terrain type is indicated over here and other parameters associated with the SUI-1 channel. The SUI-2 channel, we have, again, high K factors. Here's the delays for the various taps, tap 2 and tap 3, and also the associated power. You can again get the power delay profile here. We have different Dopplers for each tap. And again, it's type C terrain. Here we have SUI-3, terrain is type B. And we have a lower K factor than the previous cases. Also notice the delays and also the power for each delay for each tap. For SUI-4 we have a low K factor and we have higher delays. So we're talking about higher multipath delay spreads. The multipath is again modeled with tap 2 and tap 3, and here we can get the power delay profile, and we see that the K factor is smaller, and this is for terrain type B. For SUI-5, terrain type A, recall, which is hilly with a lot of foliage, a case where we have a lot of path loss, non-line of sight in this case with the low K factors, if you will, and delay spreads, which is very high. In this case, 4 microseconds and 10 microseconds are the delays on the tap. Again, you can compute the RMS delay spread using the delay profile shown over here. SUI-6, again low K factors. The delays are large in this case, 14 and 20 microseconds. You can again compute the delay spread using the power delay profile here. Again, terrain type A with a lot of loss. In this case, low K factor with non-line of sight. In the following, we'll discuss some notes on simulating the SUI channel models. So in the discussion to follow, we'll talk about how to actually simulate the Stanford University interim channel models in a computer in order to model the channels. And the reference is actually from Daniel Baum and Stanford University. And this was based on a submission to the 802.16 Broadband Wireless Access Working Group back in 2003. They actually include also a MATLAB model, and you can easily translate that into a C model. So in the simulation, there's a few points that we need to make. Now, also by discussing how to simulate these models, you get some more insight into the actual models themselves. Again, here we're talking about the microscopic effects and not the macroscopic effect like the path loss, which we already provided the expression to compute for that. And here we're actually trying to model the microscopic effects due to multipath and Doppler. Now I need to point out that the Doppler spectrum that we're talking about here is very different than the Doppler spectrum that you get with a vehicle in motion, for example, as we derive for using Jake's model. The Doppler spectrum here is very different and is due mainly to issues regarding, like, for example, wind speed combined with foliage, trees, the carrier frequency dependence, and also motions due to traffic. So it has a different power spectral density than you would expect with a vehicle in motion at high speeds, for example, 100 kilometers per second. That's a whole different model that's used in the Doppler modeling over here, which is due to actual motion of trees and vehicles in the vicinity of the area. And this is based on empirical measurements. For example, here we show the empirical measurements at 2.5 gigahertz. And what the simulation model uses is actually a rounded Doppler power spectral density model shown over here based on this expression, where f sub 0 is a normalized frequency, which is equal to f divided by fm, which is a Doppler maximum Doppler shift. So f sub 0 is less than or equal to 1. So this is the model that's used to actually match the empirically measured data for the Doppler. And again, this Doppler is different than a Doppler shift associated with the motion of the subscriber station itself. In the case of vehicle motion, for example, this is due to motion in the environment and also traffic, but not the actual mobile station itself. This is for fixed wireless situations, so the motion due to the wind through the trees, etc. Now, in order to model the Doppler effects, we consider the fact that when we have non-line of sight or even line of sight situation, basically the received signal at the antenna of the fixed station comes from multiple sources due to multipath and scattering, and at various angles into the antenna. And as we discussed before, because of the central limit theorem, then the signal at the antenna approaches a Gaussian normal distribution, and therefore it could be modeled as a complex Gaussian process, and it would also have a power spectral density due to Doppler. But as we mentioned, in this case, the Doppler is not because of the mobility of the station. In this case, we're talking about fixed stations, but because of motion within the environment, for example, wind and tree leaves, and also traffic in the environment. So we can model the signal by a complex Gaussian with a Rayleigh distribution on the magnitude, and also a power spectral density to model the Doppler. So for simulation purposes, what we do is we actually use a baseband Gaussian noise source to generate Gaussian process X with variance sigma squared equals to 0.5, and also the imaginary part Y, also generated by baseband Gaussian noise source with normal distribution, and of course the magnitude of the complex number X plus J y, the magnitude then will be a Rayleigh distribution. Of course, we're talking about the baseband equivalent model for the waveform. In the case of Rayleigh distribution, there is no direct line of sight with the base station, so all the energy is due to multipath non-line of sight components. If we have a direct line of sight to the base station, then we have a Ricean distribution. In this case, K is greater than 0. So a large K factor means you have a component due to direct line of sight with the base station. And here we're discussing how to incorporate the K factor and what is the definition of the K factor. So again, if we have a power spectral density due to Doppler, we have, in the case where K is equal to 0 non-line of sight, the power spectral density, and the signal can be modeled as originating from two normal Gaussian distributions, one for the real part, one for the imaginary part, and their magnitude exhibits a Rayleigh distribution. But when we have a K factor, which means a large K factor, which means we have a direct line of sight also, then the total power is going to be equal to the contribution due to the Rayleigh fading and also the contribution due to the line of sight. So P equals m magnitude m squared plus sigma squared, which sigma squared is the power of the complex Gaussian distribution. And that's emphasized over here. Now the K factor is the ratio of the direct line of sight power over the power due to non-line of sight and all the multipath fading and scattering. So that's the definition of the K factor. So if we go back to this expression over here and incorporate the definition of the K factor, then we can derive the expression for the variance of the complex Gaussian process, Rayleigh fading component, as a direct function of the total power and the K factor, and also the component m, the direct component, as a function of the K factor and total power. So for example, if the K factor is equal to 0, then m is equal to 0, magnitude m squared is equal to 0, and sigma squared is just equal to the power, and of course that means that it's only equal to the components due to the fading, multipath scattering and fading, which, as we mentioned, were Gaussian distributed, and way back we indicated that that comes about because of the central limit theorem. So this block diagram shows how we can actually model this in software. So here we're going to model a Doppler fading channel model with the K factor for Ricean distribution. Again, we have a complex Gaussian distribution, so we generate that by generating the baseband Gaussian noise source for the real part and a baseband Gaussian noise source for the imaginary part. We model the baseband Doppler filter by actually taking the square root of S of f, which is the power spectral density of the Doppler. And recall that the power spectral density was modeled using the rounded Doppler power spectral density model as shown over here. So to achieve the power spectral density of S of f, we need a filter with square root of S of f. So we take the real part, Gaussian random variables, and pass it through this filter. This filter itself can be, for example, an FIR filter, or it can be an IR filter, but it has to equal to square root of S of f. So we take the Gaussian random variable for the in-phase term, or for the real part, filter it, and take the imaginary part, also filter it. So then we have a power spectral density which is S of f, and then we add the component due to the direct line of sight, which corresponds to a Ricean distribution, m sub r. So this is a complex also, one for the real part and one for the imaginary part, and add that and we get a Ricean distribution over here that also has the power spectral density that we need in order to model the Doppler. Again, the total power is equal to the complex Ricean contribution m squared, magnitude squared, plus sigma squared, and sigma squared is the variance of the complex Gaussian process with power spectral density S of f. Now defining the K factor to be the ratio of the power of the direct component to the power of the Rayleigh fading component, then we obtain sigma x squared in terms of the total power and the K factor. So this is very important because you can go back to the various Stanford University interim models and obtain the K factor. And if you have the total power, then you obtain the power for the complex rarely fading component, and you can also obtain the power for the direct line of sight component for the Rician model. So let's take an example for SUI-3. In this case, we have a low K factor, so this is typically for non-line of sight. We also have the Doppler FM, which is equal to 0.4 Hertz. Again, this is for fixed wireless network, and the Doppler is mainly due to, for example, wind and trees, leaves of trees, and also traffic within the area, and it's based on empirical measurements. We have the delay profile here, where we have the actual delay 0.5 microseconds for tap 2, 1 microseconds for tap 3, and also the power -5 for tap 2 and -10 for tap 3. Here we show the actual variation of the power of the tap delay lines for each individual tap as a function of time. And you'll notice how we have fading going on as a function of time due to Doppler. And it's plotted for tap 1 and tap 2 and tap 3. And obviously tap 3 has less power than tap 2 and tap 2 than tap 1. If we go back to the model over here, we have a K factor equals to 3. Here we see the effects of fading due to Doppler over time. Obviously the time scale is large in terms of seconds, but this actually shows that we have to take this into consideration and modeling the path loss combined with the microscopic effects, because we see that over time we can actually have deep fades, and this could cause problems in the reliability of the link. So we need to incorporate all these effects in the simulation in order to model the effects of microscopic fading effects, Doppler and multipath, and also the actual path loss. And these have to be incorporated in end-to-end simulations in order to see if we actually meet our requirements over time in terms of providing a reliable service.